Hi, I'm Dr. Diana. Welcome to Uncovering Earth. Today we're going to talk about magma. Why do you need to know about magma? Well, for rockhounds and mineral collectors, knowing a little bit more about magma might help you find more rocks and minerals. Magma is pretty much an out of sight, out of mind thing. Each of the minerals shown, and many more than these, are associated with rocks which were once magma. So learning about magma and where it's located near the surface of the earth, the rocks that form from it, can help us find these types of minerals. What is magma? Magma is molten rock below the earth's surface. It is found in the mantle where high temperatures and pressure keep the rock molten or semi-molten. The mantle makes up about 84% of the volume of the earth. This picture shows the interior of the rocky planets in our solar system, plus the Earth's moon. Each planet has a crust, which is where we live on Earth, a mantle, and a core. Although the Earth's core is molten, it is not considered magma because magma is silica rich. That means the dominant mineral is silica, whereas the core is a nickel-iron alloy. So the core of the planet is nickel and iron, plus some other radioactive elements too. The mantle is a rock which behaves plastically, which means that it can stretch and fold and bend very similar to saltwater taffy. The temperatures and pressures will also vary. So some areas will be more liquid and others will be semi-solid. The upper mantle has more magma in fully liquid form, especially near hotspots and tectonic plate boundaries. The lower mantle has more magma in a semi-solid form. Let's look at the basic structure of the Earth. You might want to imagine an onion with many layers. Everything we experience in life is on the outer layer. The outer layer has varying thickness. The crust of the oceans is where the outer layer is the thinnest. Only about 3 miles, or almost 5 kilometers, not including the water on top of the crust. So the water floats on top of this outer layer. On the continents, the crust can be much thicker, all the way up to 25 miles, or 40 kilometers in depth. The next layer down from the crust is a mantle. It extends to 1,800 miles, 1,800 miles, or almost 2,900 kilometers in depth. This is the area where the huge volume of magma exists. The magma in this area moves and circulates towards the surface and then back down again towards the core. It's in constant movement. The inner part of the Earth is the core. The core has two components, an outer, fully liquid core and an inner, more solid core. The core of the Earth also moves and circulates. This movement creates the magnetosphere of the Earth. The magnetosphere is a magnetic kind of shield that protects us from getting too much of the sun's radiation. For this class, we're focusing on magma that cools underground. In this diagram, the mantle is number 1. This is an area of liquid and semi-liquid rock. The mantle is in a constant state of motion and circulation, much like a boiling pot of water. Number 2 represents the crust on the ocean floor. This crust is thinner, and when it meets a thicker continental crust, it will subduct or move underneath the continental crust. This diagram shows oceanic crust subducting underneath continental crust. Number 3 represents the depth at which oceanic crust starts to melt due to the heat rising from beneath it. The core of the Earth is radioactive and is constantly releasing heat. The depth that the oceanic crust partially melts is from 50 to 125 miles, or 80 to 200 kilometers. The rate at which it melts depends on several things. As the oceanic crust moves downward, it takes with it seawater and the sediments that have built up on top of the crust. This mix of water and other minerals can change the speed at which the crust melts. The oceanic crust is a cold slab, so it takes time for it to heat up and begin to melt. This usually occurs when the slab reaches the mantle, where temperatures exceed 600 degrees Celsius or 1,112 degrees Fahrenheit. Number 4 represents rising magma. After the slab partially melts, some of the magma, the molten rock, will begin to rise towards the surface of the earth. It does this because of the water which was part of the melt. The hydrogen and oxygen in water become gases at high temperatures, causing the magma to rise. The magma which cools underground is called an intrusive rock. The magma stays under the surface of the earth, and it will cool in several different forms. Magma which reaches the surface of the earth has a name change and is called lava. Lava cools on the surface of the earth and can create several types of igneous rocks. People may often discuss intrusive or extrusive rocks. Igneous refers to the molten nature of the rock, and it includes both magma and lava. When magma and lava are used, they describe whether the liquid is above or below the surface of the earth. We are looking at magma in this class. When magma rises towards the surface, it cools at different rates of speed and can take many different forms. Only a small percentage of magma ever reaches the surface. The magma moves through existing rock, known as country rock, and can move along layers between sedimentary or metamorphic rocks, faults, and other pre-existing intrusive structures. The country rock melts into the magma, changing the chemical composition of the magma. As the magma rises, it melts or partially melts all of the rocks it comes into contact with. Each layer of existing rock the magma comes into contact with introduces new minerals and elements into the magma mix. As a result, each area of magma, including magma that comes out of a volcano as lava, each one has a unique chemical signature. Even each eruption of the same volcano will have a unique chemical signature. Archaeologists can use those unique signatures to find out how far tools made from obsidian and other igneous rocks have been traded. The different forms that cool represent vertical and horizontal shapes, as well as various sizes. Batholiths are the largest form created from magma and can extend for hundreds of miles. Other forms that cool are much smaller in size. Magma is classified into 4 different types depending on how much silica is in the mix. All magmas have silica, but the felsic magmas have the highest concentration of silica, while the ultramafic magmas have the lowest concentration of silica. The 4 different types are felsic, intermediate, mafic, and ultramafic. Why are there different types of magma? We want to look at the type of rock that is melted to form magma. This rock is called the source rock. Each rock type, igneous, sedimentary, or metamorphic, contains different elements and minerals. When these melt to form magma, they will mix with the existing magma to create a brand new composition, and that magma will become either felsic, intermediate, mafic, or ultramafic when it eventually cools. What is magma made of? The primary components are silicon and oxygen. I have pictured different forms of silica. One is just pure silicon, and the other one is sand. Sand is a form of silica. In addition, there are many other elements that are added to magma. The most common of these elements is aluminum, calcium, sodium, potassium, iron, and magnesium. Volatiles is another word describing elements which are added to magma, but these make a magma more explosive. Volatiles include the seawater and sediments added to magma as oceanic crust subducts, or the elements added to magma as magma rises through existing rock. Magmas can be dry, meaning they don't have any volatiles, or they can be wet, meaning they do have volatiles. This graph represents Bowen's reaction series. It shows us which minerals form in mafic magma starting at high temperatures and as the magma cools down to low temperatures. The top of the graph shows high temperatures, and we see that olivine and anorthite are the first minerals to form at these high temperatures. At the bottom of the graph, we see that potassium feldspar, muscovite, and quartz form at the lowest temperatures. We can also use this graph to determine which minerals will melt first. Quartz will be the first to melt as temperatures rise, with olivine and anorthite being the last minerals to melt. Understanding mineral formation helps us to understand how minerals form underground. I've mentioned several times how magma mixes with other rocks that it moves through and through other minerals and elements. So these graphs show two different examples of how magma can mix. And there are many other different examples too that are just a little bit more in depth than what this presentation is offering. So we're looking at magma mixing. And what happens is magma may occur in different chambers within one particular region. And as the magma moves through the rock, it may move from one chamber to a different chamber. Well, each chamber is going to have its own unique chemical composition. Then when they mix together, they will create a brand new chemical composition. I've shown you Bowen's reaction series, and I've shown you how magma can mix from chamber to chamber. Well, if we put the two ideas together, what we're going to look at is that we have this chamber of magma, and crystals are beginning to form. So let's say it's very hot, and what first forms is olivine. As those olivine crystals form, they're going to drop downwards. They're going to be heavier than the magma. They're going to drop down to the bottom of the magma chamber and create a layer of olivine minerals. What's left in the magma then is a new, different mix of elements. So then other crystals are going to form out of that new mix. And then they will move to the bottom of the magma chamber. And again, the mix is going to be different chemical composition, because these solid minerals are being removed from the magma mix. This process is called fractional crystallization. It's a process of crystal formation and settling. Remember, as the magma moves through different layers of rock, each rock has a unique chemical composition. Then that magma will cool, whether it's in place or whether it moves all the way to the surface of the earth. And that cooled magma will form a rock that has its own unique chemical composition. So in this diagram, we see like there's one form that's a number 1 and one that's a number 5, and they're close by to each other, but they're going to have completely different chemical compositions because the rocks that were incorporated into that magma were different. Of all the different forms that magma can take when it cools, batholiths are the largest structures, and they can extend for hundreds of miles. Because they are such large structures, the states and the provinces have mapped these, and they've been assessed for mineral content. Within the United States, you can look at the state geological surveys, and they will have information on the mineral content of the batholiths within that state. Within the United States, there are several different batholiths, and I just picked one area because I've been to this area. So this is Idaho, and on this graphic we see two different maps. One gives the general geological provinces within the state, and you can see the green areas on the left side graphic show some batholiths. And then on the right side graphic, those batholiths are highlighted in red. So keep in mind where these are located within the state of Idaho as we start to talk about what minerals we can actually find near these batholiths. Idaho is known as the gem state. Part of that is because of these batholiths, which are located in the state. It has a few unique minerals. The state gemstone is the star garnet. This type of garnet is only found in Idaho and in India. Aquamarine and smoky quartz are also common. A wide variety of gems can be found in Idaho, along with gold, silver, copper, molybdenum, zinc, and lead. These are all economic ores that are mined. If you're visiting Idaho, the corridor between Coeur d'Alene, Idaho, and Wallace, Idaho, is known as the Silver Valley. More than 1.2 billion ounces of silver have been mined from this one area in Idaho. And this is right on the edge of the batholith. So we were there several years ago and we got to tour this particular mine. It's open for tourists and they show exactly how silver is mined in this area. Fascinating to go through these. Definitely take advantage whenever you're able to. Within the different igneous rock types, the mafic, intermediate, and felsic, that form underground, these intrusive rocks that come from magma. The ones that are most likely to have large crystals are the felsic rocks. And these large crystals are called pegmatites. A pegmatite is any type of igneous rock with crystals over 1 centimeter in size. Again, most are composed of quartz, feldspar, and micas, and they form from the waters that separate from the magma in the late stages of crystallization, usually along the edges of batholiths. This superheated water can move for a large area outside of the batholith because remember, the batholiths are huge. They're hundreds of miles in size. So they're going to shed a lot of this superheated water to the region around the batholith. And that may be miles away from the batholith. There would be that much water that's being released. This superheated water contains dissolved ions, which then moves and forms crystals pretty rapidly. And these pegmatites can grow to many feet in length. I mean, there have been pegmatites that measure, 40, 50, 60 feet in length. Those are more rare, but you can also find other size pegmatites in the range of inches to, centimeters or feet, 1 or 2 feet. I wanted to show you some pictures of pegmatites. So the two minerals that you see that are set in kind of a white, it's called quartz albite. Those are both from Afghanistan. And then the elabite tourmaline on the right is from San Diego, California. But there are many gemstones that can be found as pegmatites or near pegmatites. So when you're looking, look for these large crystals if you're in an area near a batholith. So let's compare the geologic map showing the batholith areas with another map produced by the Idaho Department of Education showing gem locations. You'll note that on the gem locations map, I've drawn a little area kind of towards the center in red with kind of really badly drawn striped lines. And you'll notice that the red dots with numbers around that area, those are the gem localities. And a huge number of those localities are to the west or to the left side of the area that I have drawn in. That shows us that when this batholith was cooling, a lot of that superheated water most likely went towards the west. And that it enabled the creation of all these different gemstones on that side of the batholith. Are you ready to look for gemstones? This class showed you why magma and its resulting rocks are important when looking for minerals. The areas near where intrusive igneous rocks form are going to have a greater concentration of larger minerals than areas without intrusive igneous rocks. I hope you enjoyed this mini class on magma and how it relates to rock hounding and mineral collection. Maybe I'll see you out in the field.